Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Gopal Pandurangan. He'll be speaking on quantum communication advantage for leader election and agreement. He's a Morse Professor of Computer Science at the University of Houston, USA. His research interests include the theory and algorithm for distributed computing, networks, quantum computing, machine learning, and big data, and he has over 150 refereed publications. He is a fellow of the Institute of Electrical and Electronics Engineers IEEE, a recipient of the University of Houston Research Excellence Award, and a winner of the ACM PODC 2025 Best Paper Award. Over to you, Professor.
Hello. Thank you for inviting me. So this talk is going to be about quantum computing, actually distributed quantum computing, and specifically about the quantum advantages we can have for like two fundamental problems in distributed computing, namely leader election and agreement. So this is joint work with Fabien, Dufoulon, and Frédéric Magniez. So what is distributed quantum computing? So it's just the idea of distributed quantum computing is that building one large quantum computer is difficult. So it's easy to connect together a bunch of smaller computers, possibly operating on a small number of qubits, and using this network of quantum computers, you can probably accomplish more. So this is paper we wrote like long time back, which is one of the first papers in distributed quantum computing. And basically it posits like two aspects of DQC though, distributed quantum computing. One is you can use DQC to distribute centralized quantum algorithms. For example, you can have Shor's algorithm, which is a famous quantum algorithm, but instead of running it on one computer, you can run it on multiple computers, okay? Distribute it and parallelize it. The other one is you can use quantum computing to improve the efficiency of distributed algorithms or distributed computing. So for example, you can use quantum algorithms to improve the performance of leader election, which is a fundamental distributed computing problem. So in this sense, they complement each other. So you can use quantum computing to improve distributed computing and vice versa. So I'm mostly going to talk about the second aspect in this talk. And if you come to the advantage of quantum in distributed computing, there has been quite a bit of work done in the last maybe a decade or so. And what people have shown is, in fact, there is the advantage. So for example, you can solve fundamental distributed network optimization problems like MST, minimum spanning tree, shortest paths. These are fundamental distributed network problems. So you can use quantum to beat classical load bounds. And also you can use quantum to improve the performance of fundamental distributed computing problems like leader election, consensus, Byzantine agreement, and things like that. So even here you can beat the classical load bounds. So you can show that there is a clear quantum supremacy for these tasks. And as I told you, these are fundamental tasks, and there are a lot of applications for them. So for example, leader election and consensus are basic subroutines that is used in distributed computing. For example, if you have a leader election, then you can elect a leader, and that will coordinate, let's say, distributing centralized quantum algorithms. Okay, and another major research agenda that is going on in the world is building an efficient quantum internet, which is basically a network of quantum computers. And if you have better quantum shortest paths algorithm, then you can use that to get better efficiency. And of course, another application that is already being implemented and used is you can use quantum computing to get highly secure networks where you can implement secure key distribution, and you can solve Byzantine agreement, which is a fundamental problem that underlies blockchains and all much more efficiently using quantum computing. Okay, so here we can show that they do better than classical lower bounds. That means provably better, and also even sometimes overcomes classical impossibility results. Okay, so let me, any questions? I mean, please feel free to ask questions at any time. So,
So hello, sir. Uh, Sorry for interrupting initially. Sir,
yeah.
I rough and I'm very sorry if I'm asking a dumb question as well. Here, I heard that especially in quantum computations, when you are using qubits to do the computations, I heard
Right.
that after computing, if you are transferring also, these qubits will change. Is that correct, sir? Or
No, the qubits are not changed. They're just transmitted though. Yeah, that's the assumption. We'll come to the model. So, yeah, so that's why, I mean, let me look at the model though. So this is the model that we
okay,
are going to use. So this is the classical network model where you have a communication network, and like we're assuming there are n nodes which are network, I mean, processors are just computers, and there are communications links between them. And in each round, I'm basically going to also assume there are m communication links. So n nodes and m communication links. And in each node, in one round, it does some local computation. It sends messages, usually of small size, to each neighbor and receives all incoming messages. So this is a standard model of distributed computing called synchronous model. So it operates in lockstep. And the two fundamental complexity measures in distributed algorithms is, or distributed computing, is number of rounds to finish the algorithm and the number of messages, the total number of messages exchanged. Okay, and that's basically the classical distributed computing. But let's see how you can augment that with quantum computing. So in quantum, what you have is you can have like the local computation need not be classical. It could be it could be quantum. The memory also could be quantum. So for example, if I have some, so a node can have some register, okay, and let's say it takes values. Let's say it can take 3 possible values. So in a randomized algorithm, okay, so that's why in some sense you can think of quantum computation as sort of generalizing randomized computation. Okay, so in randomized computation, so you can have like a probability distribution over these 3 states. Okay, so for example, with probability 1, so probability P1, it can be in state 1, and P2 state 2, and so on. And of course, the sum of the probabilities is 1. So this is probably how you choose. Probably you choose a random state with probability equal, maybe with equal probability. Okay, so that is randomized classical. So in quantum, what you can do is you can have the same. You can still have the states in a probability distribution, but it's not where the A's are not actually probabilities, but square root of the probabilities, or rather the squares of A1s, which are called the A's, which are called amplitudes, sum up to 1. Okay, so that is basically in a very high level nutshell, that is basically the difference between like quantum and classical. Okay, and of course, since the sum of the probabilities are not 1, so since the squares are 1, the quantum computation or quantum registers, which is how computation is done. I mean, you keep changing the data in your local memory, right? That's what computation is. It evolves through unitary transformations. So that's why you keep multiplying by unitary matrix that preserves the squares property. The squares of the sum of the squares of the amplitude should be 1. So that's what happens to the local thing. Okay, so what happens to the communication? So that is the computation part of it. That's what happens within a node. So now I'm assuming where you're putting together these quantum nodes, okay, by a network, connected by a network. So, and of course, you are assuming this local computation could be quantum. It could be classical also. The computation local can be classical also. You can see that quantum generalizes classical, right? So, and there's a way to do that. So you can take all classical computation and make it quantum by making it unitary, basically. Okay, so but the point is they are also connected by a network, and we are assuming what is called as the congest model. So in the congest model, you can only send messages of small size though, right? So that means like, let's say log n bits, where n is the number of nodes. So you can only send the IDs, for example. To even know the ID of a machine, you need about log n bits. So you can send small message of small size, right? So, and of course, these bits could be like just classical bits or qubits. Okay, so in general, they can be qubits. And generally, till now, till the work that I'm going to discuss today, I mean, it was published last year in PODC 25. So generally, people have assumed that the bits themselves are transmitted classically, right? So you determine which edge to to communicate over, okay? And again, just like classical, you can have the two fundamental complexity measures are rounds, the number of rounds before the algorithm terminates, and the messages is the total number of qubits exchanged, right? So, and that is in a nutshell, that is the model. And again, as you said, I mean, you can transmit. So, I mean, we can come up with a more detailed model, but that's basically it. You can transfer qubits, and the important thing is that you can. I mean, you will see that you can even transfer the bits in superposition. I'll come to that. Okay, but this model has been already used. Okay, and there's been quite a few works in this model. Okay, and now you can ask. Now, since you can do local computation, right, and then you can also send qubits. So what can you do? I mean, what is the extra advantage that you can get? Okay, so what you can show is that there is no real quantum advantage for many fundamental network optimization problems. Okay, so, and this was one of the results that we showed earlier. This is one of the first papers in this distributed quantum algorithms area. So it's a kind of negative result showing that even if you assume prior shared entanglement, there is no significant advantage. That means like quantum distributed algorithms are almost the same round complexity as classical for these fundamental problems like minimum spanning tree, shortest paths, and things like that. Right, and this even assuming pre-shared entanglement. So this is another thing that I did not mention. But for example, you can start with already you can have shared entanglement bits entangled between the nodes. So in some cases you have to pay the communication cost for that sharing. But sometimes for lower bounds, for example, you can even assume that they are already shared, right, magically. So you don't penalize that. So that is part of the pre-processing cost. But even with that, you can show that there's no quantum advantage. Okay, so it's a pretty strong result though. But so after some time after this paper, then actually I think after 4 years, like Legal and Magniez, and then after that a bunch of papers showed that in fact there are problems where you can get quantum advantage. Okay, so and this is for problem. I mean, the most famous, I would say, the important is the diameter, computing the diameter of a network. So given a network or a graph, you have to compute the exact diameter. So that you can show that quantum will do better in general or classical. Okay, and this even without assuming any shared entanglement. So this is the exact model I was saying earlier. Okay, that you can only send qubits. Okay, and that's sort of the status. Okay, as far as rounds are concerned. And now the question is other quantum advantages. Okay, so the main focus of this current talk is about message complexity, and the idea is, can we also get advantage with respect to message complexity? That means the number of quantum bits transmitted, which is the message complexity of a quantum algorithm. And so basically, there's not much work on this aspect, except there's a paper in ICALP, like in 24, that shows that you can improve the message complexity of fault-tolerant consensus. Okay. And in all these works, as I mentioned earlier, the messages are controlled classically. That means once you have a qubit, you can only send along which link to send is controlled classically. Yeah, so a node can have 10 links and you can choose one of the links, or that is controlled classically. So the main point of this paper, this work that I'm going to talk about, is that we introduce a new model where we assume that the message, which could be classical or quantum, can be transmitted with so-called quantum routing, right? I'm going to talk about it next, okay? And we show that with this quantum routing capability, you can get significant quantum advantages, okay? So that is sort of the main gist of the talk, though. So any questions? Okay, so here, this is one thing where, we'll talk about the modeling, so it maybe explain things a little bit better. So in this model, so this is exactly the same thing, but let me just give you the intuition for, or like the motivation for why quantum routing, right? So in quantum routing, basically I can send a message in superposition, okay? And this kind of thing has been done in physics. Okay, so and there are more and more works going on in physics. But in a nutshell, if you look at this diagram, right? So basically, what's happening is that, so let's say I can send, I can send a photon from this endpoint, okay, to from the left corner, bottom left corner to the top right corner, and I'm sending only one photon, and this is like the double slit experiment. So so there are two. You can think of them as two basis states. Like it can go completely right or completely up, or it can go in superposition. So for example, you can so it's the same photon, but it's as though it's like it's going in it's in superposition. For example, if you have 1 by square root of 2 phi is the state, so that state can either go up or it can go right, and that transmission could be in superposition, right? It could be equal. It can occur with equal probability, and of course, if you measure it, it will collapse to one path, right? But when it is, that's sort of the main sort of phenomena that people initially found in quantum, right? I mean, this is basically the earliest double slit experiment. But now people have looked at it and they've tested it and all, like physics people. Okay, and this is the model we assume. So, for example, in general, what happens is, let's say I have node V, right, and it has two links U and W, for example. It could have multiple links, but let's say it has two neighbors or two links where it can send messages across. So we can send a single message, but in quantum superposition, right? So earlier, the classical routing is still a quantum message, but either you can send it to U or W, right? Or both. Generally, people in distributed algorithms, you send both. You send the message to all your neighbors. And so in that case, that is fine if you're only caring about rounds, right? So now we want to be sublinear in the number of messages. So you won't even save on messages. So here I'm only sending one quantum message, but in superposition. That means, let's say some probability with probability amplitude alpha, I'm sending along link U, to U. And with probability beta, I'm sending along link W. That means the link that goes to W. Okay. And of course, if I measure it, it will collapse to the appropriate probability, which is the squares of these amplitudes. So until we measure the let's say the message, for example, until V or UW, one of them, whoever measures it, it's still in superposition. Okay. So this is in a nutshell what quantum routing is. It's just generalized as classical routing. Okay. Any questions? So, and this is basically the full quantum controlled distributed network where you have quantum local computation. You can send messages of small size only, we are going to assume. So there is a model where you can send arbitrary messages. So it's called the local model. So this is called the congest model, which is these two are the two standard models in distributed algorithms or distributed computing. And here we are assuming only small size messages can be sent. And you are assuming quantum routing. That means the messages can be quantumly controlled. That means it can be sent in superposition. And you can similarly define message complexity. So message complexity is simply the number of messages sent, right? So if I send one message across to 10 neighbors, it's still one message because it's sent in superposition. Okay, so just like classically, right? So in classically, I might choose one node randomly and then send it to that, right? Here, it's the same thing, but it's in superposition. It's still counted as one message. That's the main model. Okay. And what you're going to do is we're going to study two fundamental problems. These are like sorting or whatever. Like in centralized computing, sorting is a fundamental problem, right? So these two are sort of the fundamental problems in distributed computing or distributed algorithms. So what is lead election? So lead election is you have a network, and you at the end of the algorithm, only one node should be a leader, and all the rest should be non-leaders. And that's lead election. It's been studied for like maybe 50 years. And agreement is the year we consider a simplified notion of agreement, where in the agreement problem, each node starts with input, like a 0 or 1 input. That's the input value. And then at the end of the algorithm, all the nodes, at least all the nodes that decide, should decide on the same value, right? So, I mean, it should either Z, all of them that decide will either choose 0 or 1, and some nodes may not decide. Okay, in that case, they just output, I'm not deciding. Okay, they output empty, for example. And but the point is, all the decided nodes must agree on the same value which must be the input value. Okay, so that means if they all decide 0, then at least one input value should be 0. Okay, if they decide 1, at least one input value should be 1. Otherwise, the problem is trivial, right? Because I can just decide all on 0, right? So that is the implicit agreement problem. Again, this problem has been studied for more than 50 years. It has won many Turing Awards are part of it. So the Byzantine agreement, which is where some nodes can be malicious, is the fundamental problem that underlies blockchains. So in this paper, I may not talk too much about it. We're not assuming the nodes are Byzantine. The nodes are all good, and the question is what is the cost for doing this? What is the complexity of agreement? Okay. So let's look at some of the work that was already done before. So in classical distributed algorithms. So we are going to look at the messages, not rounds. So the focus on messages. So you can show that for complete networks, the messages there is a distributed algorithm that elects a leader in a complete network, which is very studied quite often. Just whether complete means what? All the nodes are connected to each other. And the message complexity of this is square root of n, and this is tight. So this we showed about 10 years back. That means square root of n is basically a lower and upper bound. And similarly, for diameter 2 networks, like you need about theta n messages. Again, n is the number of nodes in the network. And for general networks, you can show that means for diameter 3 and beyond. So you need theta m messages. M is the number of edges, or the number of links. Okay, and for agreements, this is for lead election. For agreement, what you can show is you need at least square root of n messages if you only allow private randomness, and if you allow shared randomness. So shared randomness is a little bit like entanglement, right? But this is still classical. So the shared randomness between the nodes which is assumed. If you assume that, then you can do better. You can do better than n to the square root of n. You can do n to the 0.4 messages. So these are already known results, okay? And the question is, can we improve them? And in this paper, we show we can improve them, okay? So, and that's the main results, okay? This is the only thing you want to understand. This is the main result. That means if you use quantum routing, in this quantum routing model, then you can beat the classical lower bound of square root of n and get n to the 1/3 for complete network. And this is the main result I'm going to talk about, though. Because that, in a nutshell, at least it gives you the fundamentals of what distributed quantum computing is, okay? In this, distributed quantum algorithms are, okay? And similarly, in diameter 2, you can get instead of n is a classical lower and upper bound, tight, and you can here get n to the 2/3, okay? And similarly, for general networks, instead of m, you can get square root of mn. And expanders, you can get something, okay? That is, I'm not going to talk too much about it. And similarly, for implicit agreement, the best known classical is n to the 0.4. Here we get n to the 0.2, right? And this gives you a framework, and I would say the more important contribution of the paper is it gives you a framework for doing this Grover search, which is a fundamental quantum algorithm in the distributed setting, especially in the view of improving messages and all. Okay, so it gives you a framework for doing distributed Grover search and quantum box, which I'm not going to talk about. It's another important tool in quantum algorithms. So how do you do this? Because we use these two fundamental techniques to improve the message complexity or the communication cost of algorithms in the distributed quantum setting, right? So that is the main point. That is the main that's a bigger contribution. So any questions? Okay, so the remainder talk, I'm going to talk mainly about complete networks. So I'll talk about a little bit about diameter 2. So what is the ideas that are used? Okay, so first we have to look at Grover search. So of course Grover is probably maybe the only 2 or 3 important quantum algorithms. Shor, Grover, and Grover is definitely one of them though. Okay, so and it basically is an algorithm for this fundamental basic search problem. Okay, so you have a finite set. Let's look at it abstractly. So you have a finite set, and the idea is there's a function that maps x to 0, 1. Okay, and let's say EF is the fraction of nodes in this X, fraction of elements in X that evaluate to 1, where the function evaluates to 1, right? So basically search is to find one such element. Okay, that's what you find. You want to find an element in X that evaluates to 1, and let's say EF is the fraction of such elements. And I won't do this in a distributed way though. Of course, classically this is what Grover solves. So, and in distributed, let's look at what happens. So let V be some fixed node in the network, okay, and that wants to find some X, okay. So this X set X is there. It wants to find some X such that f of X equals 1. That's the same goal as in centralized. And now the node, but I'm going to assume that node V must be able to compute for any input X, right, the value of f of X. This is again standard, and same in centralized. I have to know how to compute f of X, okay. And the question is, I want to minimize the number of these computations. I don't want to look at every element in X and compute f of X. That would be too costly. Okay. And this computation in centralized, you will typically assume this is the number of queries to the function or number of computations to the function. That is just one cost. One query is one cost. Here, I'm going to assume that that is going to cost me TC rounds and MC messages. And this checking is called so this checking the value of f of X or computing the f of X, whether it's 1 or 0. In fact, you don't even have to compute it. Either it's just 1 or 0. So checking whether it's 1 or 0 is done by this algorithm called checking, which is a black box. Okay, this could be even classical. So typically even this algorithm is classical. Okay, so in certain settings. Okay, and now the question is, if you have this thing, what is the complexity of Grover search? Okay. And this is based on what is called this more general Grover search, which is called as amplitude amplification, quantum amplitude amplification. So let's look at, so the best way to understand this is by looking at what happens classically and then see what happens quantumly. Okay, so classically what you do is you want to find that X such that f of X equals 1. What do you do? The simple strategy is randomized. You sample an X and check whether f of X equals 1 using checking, right? And checking typically can have some cost. I mean, it's the cost of computing that function. Okay, it could be unit cost usually, but that's a cost. And since I sample it, the success probability is exactly epsilon f, because epsilon f is the fraction of elements in X that where f of X equals 1. So if I sample randomly, that's the probability I'll find it, right? And that I can boost it to any alpha. So any 1 minus alpha, where alpha is the error probability. Okay, so I can make this 0.99, that is alpha is, let's say, 0.01. And the number of iterations I need is this. That means I keep on sampling so many times, right? I keep sampling. This is just simple probability calculation. Okay. So this many number of iterations I need, theta log 1 by alpha by epsilon f iterations. So this is just simple probability calculation. And the main point of Grover, so this is what is called amplitude amplification, is this. Okay. So in quantum search, I can do quadratically faster. So this is the magic of quantum. So instead of doing so many iterations, so basically what I can do is I can do the same search in log 1 by alpha. That is there. You can see log 1 by alpha is there both in classical and quantum. But instead of epsilon f, you have square root of epsilon f. Basically, epsilon is lower bounding epsilon f. Okay. So you can think of epsilon as epsilon f. So instead of epsilon f, you have square root of epsilon f. And of course, this is the cost you have to pay for one checking though, right? So it's TC is the cost for checking the number of rounds, and the number of messages is MC. Okay, so here I'm assuming unit cost, so that's why I don't pay for it. But that's okay, so that's for one checking, and so you have to do so many checkings, so many iterations, and that's why that is the cost, right? And this will return the same thing with probability at least 1 by alpha. So the guarantee is exactly the same, but you do quadratically less number of checkings. Okay, so this is a general result, and this is one of the, I would say, one of the fundamental results in quantum algorithms and quantum computing. Okay, any questions on this? Okay, so this is just taking the standard Grover search but casting it in the distributed setting. Okay, and now you can look at a simple example of this this distributed grower search, right? So let's say I have a simple graph, which is a star graph. There's a center node V, and there it has, let's say, n minus 1 spokes or leaves attached to it, right? So let's say the star node, every node starts with a bit, okay? And basically the center node wants to find some spoke node that has bit value 1, right? So, okay, initially they all start with some arbitrary bits, right? Classically, if you want to do that, I have to communicate n messages because any node could have that bit. So I have to send that message to everybody, right? I have to communicate. V has to talk to all its neighbors. So it will take n minus 1 messages. So in quantumly, but by using this distributed grower search, I need only about square root of n messages. Okay, how do you see that? So that is the nice thing about using that framework. So you can almost do it as a black box, right? Because classically, what I will do is I'll implement this checking algorithm. V will send a message. Let's say V randomly samples a message, right? And that takes 2 messages because you have to send it and then receive the check what the reply, right? Whether it's 1 or 0. And that takes 2 messages. And what is the success probability? Since there could be just one node with 1, right? The success probability could be, can be as small as 1 by n minus 1, right? So that is the classical success probability. And now the nice thing is you can plug that into grower and you get a quadratic thing. So that's why you can almost apply it as a black box. So for this to apply, you don't even need to know what quantum is. So if you have a success probability that is whatever in classical, you can amplify it to quadratically better, right? So now the success probability becomes 1 by square root of n minus 1, or basically square root of n. So that means if I do one checking, which involves 2 messages because I have to send and receive back, because that's what I'm going to do this in superposition though. That's what grower does. It will take care of that. So I need only square root of n checkings. So because the success probability of one checking is 1 by square root of n. So I have to do this about square root of n times to get the message, right? So of course, this is impossible classically. So you cannot do this in square root of n, but using this in the quantum routing model, you can do this because you're doing this checking in superposition, okay? So let's look at this in a little bit more detail though, okay? So let's say I have this U, okay? So let's see, because I'm going to see where do you do this grower search, right? So this gives a little bit more details, okay? So I have the star graph. So, okay, so each leaf has bit value this xv, and you want to find the leaf with xv equals 1, okay? And in sequential grower search, what you do is basically you're going to adapt sequential grower search, okay? So you're going to start with the state in the center node, okay, U, and let's say which is a superposition of all possible sort of transmissions, right? So you can think of a state V as being the state where U transmits to node V, okay? And classically, I can just do one, right? Here, I can do it in superposition, right? So note that this means what? All possible transmissions are equally likely. That means there's in uniform superposition. So note that 1 by square root of n is the amplitude. And if you know grower, it's what grower consists of 2 things, right? So you have to do 2 operations. So one grower iteration is 2 operations. One is this reflection, right, which is basically the grower diffusion operator D, okay? So that grower diffusion operator is applied locally and the center node, okay? But the second operation, which is called phase flip, is done at the leaves, because the leaves only know whether it's 1 or 0, right? So what does the phase flip does? So it basically reverses the thing, right? So what is the strategy? So locally in the center node, I do yes, and I do the grower thing, and I send that, and I implement this phase flip, right, using this checking. So that is what checking is. So the phase flip is implemented by checking using 2 messages. So what is phase flip? When a node receives a message, the node that has 1 will flip the face of it. So this is the basic grower thing, right? So you can see that V in this oracle, the phase flip thing is going to reverse that. If it is 1, it will be 1 minus 1 to the power xv. If it is 0, it's not reversed. V is left as V. But if it is 1, then it becomes minus V, right? The state is flipped and that is sent back. Okay, so this is all happening in superposition. Okay, and this is basically, that's why you can, this is what I just explained is one iteration, and you have to do, Grover does it only, need to do this thing square root of n. As you keep doing this, the probability of finding that node with V will increase to close to 1 if I do it square root of n times. If I do it 1 times, the probability is 1 by square root of n. So that is in a nutshell what Grover iteration is. Any questions? Okay, so in rest of talk, I'm going to talk a little bit about this. Okay, so mainly I'm going to talk about how can I use this this Grover distributed Grover search to improve leader election. Especially, I'm going to talk about complete networks. And the good thing about this whole thing is that if you understand this, if you plug this, if you use this, you can use this as a black box, the distributed Grover search amplitude amplification, to get improved quantum algorithms, even if you don't know anything about quantum, just classical. Okay, if you know about classical. So let's look at leader election and complete networks, and this is a good example of how we can use it. Okay, so first let me talk about the simple, I mean, an algorithm is quite simple though. So this gives you the optimal square root of n. I told you in classical, the optimal message complexity is square root of n. That's tight. Okay, and this is how you can do it in square root of n. Okay, instead of n. So it's easy to do it in n messages, but here you can do it in square root of n. Okay. So how do you do this? So each node will become a candidate with some small probability, log n by n. Okay. So this ensures that at least there'll be one candidate. Okay. So only candidates will become leaders. So this already cuts down a lot of messages. Not everybody will try to become a leader. Okay. Initially, I'm assuming that everybody wants to be leader. Okay. So that I'm assuming that's standard. And so now what's going to happen is each candidate will choose, let's say, a random number between 1 and n cubed. Okay, and we can show that this will be unique. Okay, and what is this algorithm? It has only, this classical algorithm has only 2 rounds. Each candidate will send its rank to about square root of n neighbors, chosen uniformly at random. So in classically, I choose them uniformly at random just by sampling, right? So that means each node is sampled with probability about 1 by square root of n. So it's about square root of n neighbors are sampled, and you send your rank. And in round 2, what happens is that each node that receives any rank in round 1, okay, replies to all messages with the highest received rank, right? So basically, these nodes act as referees. So the referees will say because what is the idea here? The candidate with the highest rank will become the leader. So the idea is to eliminate all other candidates with lower rank. Right? So a referee which receives multiple ranks will say, okay, you are the one with the highest rank, the others, you are not. So obviously they will not become leaders, right? So the any candidate that does not receive any higher rank will not become leader. Okay. So that is the point. Okay, that means the highest rank will become leader. Okay, so this is a very simple algorithm. And note that you can see that it takes only square root of n messages. Square root of n log n. So that's why I said about square root of n, because there are log n candidates, the high probability you can show, and then each of them is sending about square root of n. And the reason why it works is because of this handshake. So now you can wonder why square root of n is enough, right? The point is square root of n, this is basically the birthday paradox. This is a very basic paradigm in randomized algorithms. So basically what I have is, let's say basically what they're doing is they're solving this so-called handshake problem, right? So let's say U and V are 2 nodes. Let's say U has higher rank than V, or rather U has the highest rank. So the highest rank will obviously become a leader, right? Because nobody's higher than that. But all other nodes should not become leaders. That means they should intersect with one referee. So U is sending to square root of n referees. Those are the middle nodes. And V is also contacting square root of n nodes. So if I do square root of n, then with high probability, this is just the birthday paradox, one of them will intersect. One of the referees of U and one of the referees of V will intersect. And we will get the message that it's not the highest. Right? So that is the idea. So now we can show with high probability, all the nodes that are not highest will be notified that they're not the highest, and they will not become the leader. Right? So because the criteria for leader election is exactly one node becomes leader. Right? So that's what it's doing. So basically it's solving this handshake problem between every pair of nodes, but they're only about log n nodes, and so they're about log square n pairs of nodes. So approximately this will take about square root of n log square n, sort of. Handshake. So yeah, so log square n handshake computations, and that's why it takes about square root of n times some log messages. So any questions? Okay, so and now, yeah, so that is the referee, okay, which will, for example, that one common referee will tell you that, okay. So this is classical leader election. Now the question is, how can I, so this is the correctness, what I just explained, okay. So, and how can I improve this using quantum, okay. So in quantum, it's the same thing, right? The algorithm is exactly the same, at least the first part. So each node becomes a candidate with the probability log n by n. Right, and this will ensure that there on average there are about log n candidates, so it means at least one candidate with high probability, and each candidate chooses a random rank. But now this is where there's a difference. So each candidate now sends its rank to k neighbors chosen uniformly at random. So this is also classical. So in fact, the setup, all the 3 rounds are classical. You can do it classically. Okay, so each candidate now chooses sends its rank to k randoms, but k is now it's a parameter. We'll fix it at the end of the algorithm. We'll choose the best k to optimize the message complexity. So it chooses k neighbors chosen uniformly at random. Okay, it sends it. So these are so there are k referees for each node. Okay, so the only quantum thing is in the second part. Okay, in comparison. So in round 2, so this happens because Grover takes square root of n rounds to check, right? Because I have to do it one at a time. So that's why this will also take so many rounds. So what we'll do is every candidate now will quantumly search. We'll do distributed quantum search to check whether there is some other node with a higher rank. This is exactly a search problem, where the function is given my rank, is there some other node which is higher rank? So that is the function I'm looking for. That is the function I'm searching for or evaluating, right? And now I'm going to, and how do you do this? And why is this? And the goal is I'm going to claim that I need to only send about square root of n by k messages to search. Basically, every node searches so many messages. Sends so many messages to do the searching. And the algorithm is the same. Any node that did not find a node of higher rank will become the leader. Okay. And let's do this. Let's do a simple analysis using Grover search. Okay, distributed Grover search. So correctness is easy, as I had argued classically. Right? The node with the highest rank will not receive any higher rank, obviously, because it's the highest. So it will become the leader. So what you have to prove is no other node becomes the leader. That means it will get a no winner notification. That means there is a referee that will find a node with higher rank by the search, right? Because every node is trying to find a node with the highest rank, with the higher rank, right? So what is the probability of that? So so what it is doing is it's searching if there's a node U, right, which ranks strictly higher than its rank. And classically, how do you do this? Classically, what is the probability? The probability of finding such a node is k by n, because there are k referees that the highest rank computed. If I randomly search, the probability of hitting that referee is k by n, right? And you can use Grover search as a black box. Now the success probability in the classical is k by n. Now that is quadratically amplified. Now the success probability becomes square root of k by n, right? That is the Grover thing. Epsilon is k by n. So you put epsilon here and it becomes square root of epsilon. So it becomes, so the success probability is k by square root of k by n. So the number of times I have to do is square root of n by k, right? And then it'll take so many rounds though. It's slower than classical, right? Because I have to do it slowly, okay? But the number of messages is only this, right? Because in each checking, I only send 2 messages, right? So the total message complexity is what for the entire algorithm? It's k, right? And I'm multiplying log n because there can be log n candidates. So each log n candidates can be sending k. So that's why this tilde is basically hiding the log factor. So basically I'm omitting the log factor. So it's k for the first round and square root of n by k messages for searching basically in the second round or in the second phase, right? And the best one that optimizes this is k to be n, k is n to 1/3. So if I use k, if I plug in this is the optimum thing that optimizes this thing, I get n to the 1/3. And the round complex, so this is much slower. So the classical takes quite often messages, but it takes 2 rounds, right? Right, 2 rounds. So here it takes rounds as many rounds as number of messages. So it's slower though. So we don't know how to make it faster. We conjectured this is probably not possible if you want to get this message complexity. Okay, so that's the whole point in a nutshell though. So any questions? Okay, so this is the main, I would say the main technical part of the talk though. Okay, and this, I mean, the paper has much more results, but this is the main thing that gives you the idea of what you can accomplish with quantumly in as far as message complexity is concerned though. So if you care about rounds, this is worse. In fact, this is worse than classical. So here we are only looking at the number of qubits. So this is the number of qubits that needs to be transmitted. Okay, so okay, so I can also look at, so you can generalize this idea to get a better thing in diameter 2 networks. And this is again, I think it's a good example of another application of this distributed grower though. Okay, so let's look at a diameter 2 network. So we looked at a complete network. Everybody is connected to everybody. Okay, it's a clique. So in diameter 2, it's not a clique. It has diameter 2. So, but you can show an easy property of diameter 2. Since the graph is diameter 2, every 2 nodes should have a common neighbor. Okay, so that is a simple property. Otherwise, diameter will not be 2. Okay, so, and in centralized, in classical, you can get a O tilde n message algorithm. Okay, and this is quite easy though. Okay, and this is also tight. You need n messages. The lower bound is slightly, it's a little bit tricky, but the upper bound is easy to get O tilde n though. Okay, because of this property. Okay, and again you have to solve this handshake problem. The idea is similar, so you have to, so again node, the algorithm is almost the same. So a node selects some number of neighbors and sends its rank, right? All the nodes do that, all the candidates do that. Again, I choose only log n candidates by sampling, self-sampling. Okay, and if there is a common candidate, let's say this W is the referee, so you will send, so you and we meet at this referee, right? So W will say which is better, which is higher. So the lower will lose. The highest will obviously win, and all the rest will always intersect with the highest in the referee. So all the others will lose. So that's the idea. The question is how many messages I should do for it. I should spend to get this handshake in diameter 2. Right? So what you can show is by just doing this distributed Grover search, which I just mentioned, basically if I apply the leader, like the complete network idea, I can get n to the 3 by 4, n to the 3/4 messages and rounds. Okay, so this beats the classical, because the classical note that n is tight. You cannot get better than n. So here you get that. There's a more involved algorithm though that I'm not going to even mention now. So using quantum box. So using quantum box, you can get n to the 2/3. Right. So quantum box is more like, it's another very nice technique, but it's more involved than Grover search. Okay, so you can think of it as a more generalized Grover search in a network, but it's definitely out of scope for this talk though. Okay, but let's see how to do this. This one I can sort of explain. Okay, this 3 by 4. Okay, so the idea is exactly the same. It generalizes this. So again, the idea is to find this handshake, to do this handshake between pair of nodes. Since there are only log n pairs, so everything will be multiplied by some log factors. Okay, so I just have to do one pair, right? So idea is, let's say I have 2 nodes, okay, and I have to find a common node. Okay, so the idea is what you will send about square root of n, a token to square root of n random nodes. That means it'll send its ID though, its rank to square root of n random neighbors. Okay, and we will search for that. We are searching for a node with higher rank, right? So it's going to search for that, whether there is a node with higher rank, right? So let's say I use the highest rank, so we will has to intersect that. It has to find that one of these k or square root of n tokens it has sent. But the point is, unlike the classical, you and we could have only one common neighbor. right? So because in diameter 2, there should be one common neighbor, but there can just be one, right? In clique, there are almost all the other neighbors are common, but in diameter, it could be like this. So this is a diameter 2. I mean, this could be in diameter 2, okay, where the nodes are, there can be only one common neighbor between two nodes, okay? And so in this case, what could happen is that when you send square root of n messages to its neighbors and B searches for it, the success probability is 1 by square root of n, right? Because that could be just one common neighbor, let's say W, right? So the probability that if V samples it, V finds such a thing is 1 by square root of n, right? And then the success probability is now amplified quadratically, right? So because just assume the Grover search in a black box, right? So basically I have to do n to the 3/4 messages. Why? Because in everything I have to send square root of n. Every time you will send about square root of n and you search for it, right? Because the success probability is now 1 by square root of n. Again, why is 1 by square root of n? So you sensed about square root of n nodes, right? And this has to get that, right? So this has to get the probability of hitting one of them is square root of n by n at least. So it's 1 by square root of n, right? So this will give you n to the 3/4 messages and rounds. Okay. So, and that's basically the summary of the talk, though. I mean, so basically we looked at this quantum model, routing model, and for communication efficient quantum algorithms. And so I talked about Grover search, but you can also work with quantum box. You have to modify quantum box again for distributed setting. And that's on the main contribution of this paper, though. Okay. Any questions?
Thank you, Professor.
Yeah.
Thank you for accepting our request and delivering a very interesting talk. Are there more questions from the audience? So I guess there are no questions. Thank you again, Professor. And thanks everyone for attending the talk.
Okay. Thank you.
Yeah.
Bye.